right, well, I'm actually going to discuss the relationship between these three topics, and gambling is going to play a significant role. I didn't just throw that in there to make the title sound more exciting. But let me just preface this by, this is a quote from Alan Turing. This is from the proceedings of a conference on information theory, which took place in London in 1950. And what he says is, in many types of investigation, for example, in the theory of information, it is a useful assumption that, quote, computation costs nothing. It is important, however, not to let this assumption become a belief. In particular, when one is considering brains and computers, the assumption and the theories based on it are not applicable. All right, so it's quite impressive that back in 1950, first of all, that Alan Turing was considering the issue that, when we're talking about computation, the cost is a significant consideration. And then specifically with respect to information theory, the cost of computation is something that's important. So really, the main focus of the talk, or the main point of this talk, is to get some more understanding about computational information. The kind of encryption I'm talking about is going to be very simple. And if you're cryptography, you probably know that there are a lot of applications of computational information to new ideas like leakage-resilient cryptography and deterministic encryption. And I'm not really going to be looking at that. I'm just going to be looking at the most basic kind of encryption scenario we can have and see what we can say about it in terms of computational information. And please stop me at any time if something that I'm not saying isn't clear. So here's our very basic encryption setup. So we have three parties involved: Alice, Bob, and Eve. And Alice wants to send a message to Bob on a public channel, and Eve, that channel is public, and Eve is able to listen to anything that's sent over the channel. So what we're going to do is suppose that we have the following. We have two functions, an encryption function and a decryption function. And how do these work? Well, first of all, in this setting, this is called the private key setting, before any message is sent, Alice and Bob need to share a key with each other. Now, Alice has a message X, and she gives X as well as the key K as inputs to the encryption function. That produces something we call a ciphertext, Y. The ciphertext is transmitted over the channel, and then finally on the other end, Bob is able to apply the decryption function to the ciphertext along with the shared secret key, and to get X back out as output. Now, of course, we're talking about Alice and Bob of having this goal of sending the message secretly. So in some way, we want to be able to characterize what it means that when Eve listens to this public channel, somehow by seeing the ciphertext, she doesn't learn anything about the plain text X. So just as a setup, we need some notation. So we're going to have three sets here. We have a set of messages or plain texts. Those are the inputs to the encryption function. We have a set C of ciphertexts. And we also have a set K of keys. Now, when we're not working in the computational setting, we could just let these be arbitrary finite sets. When we look at the computational setting, we'll typically assume something like these are all sets of bit strings. And even, yes?
The ciphertext, the ones that get encoded, is that what that means? Or?
The ciphertext is the thing that's the result, the output of the encryption function.
The encryption.
Yeah, yeah. So Right, and so we may assume, in some settings, we'll just leave these as fixed values. Sometimes we assume that n varies, and in that case, m and c are say, polynomial are bounded by some polynomial in n. So we'll be going in different settings. We'll treating these in different ways, but that's sort of the most general thing that we can think of. And yeah, now as far as what these represent, our encryption function then is a mapping from keys and plain text into ciphertexts. The decryption function maps keys and ciphertexts into plain texts. And we always want to have this basic correctness property that for any k and any x, if we encrypt x under k, and then we decrypt it, we just get back what we started from. All right, so now we come, this is just the very basic setup. We come to the question of what it means to have some kind of security. And the first time this was really considered in a systematic way was by Shannon in 1949 in a paper called Communication Theory of Secrecy Systems. And of course, Shannon is working just at the time, just a few years after he's published his seminal work on information theory. And he basically uses ideas from information theory to be able to characterize encryption security. So in this setting, the first thing that Shannon does is to say, well, let's assume that all of our sets here come equipped with some kind of probability distribution. So I'll use Roman letters to correspond for the distributions on these sets. And for our purposes, we're always just going to assume that the distribution on keys is uniform. The distribution on messages is something that's given to us, say, a priori. And then once we have these two distributions, that induces a distribution on ciphertexts. Right, the ciphertexts are, a random ciphertext is what you get by selecting a random message and a key and encrypting the message under that key. All right, so now.
Could I just ask, when you say the m is given, how should we think of this? Is this
well, for example,
how frequently, how we speak, or how we?
Yeah, it could be. Yeah, say English. There would be some distribution associated with English, but we're going to treat it in a much more abstract way. Okay. So Shannon just says, well, let's just suppose that the messages come equipped with some distribution. Okay, so what we first need to do is to give a definition of entropy, Shannon's definition. So here, let's just let x and y be any two random variables. And we'll define the entropy of x as being the expectation of the negative log of the probability that x takes on a particular value. And then there's a conditional version of this. All right, now, there's some intuition about what the entropy means. I think it means different things to different people in different settings, but somehow it's supposed to be a measure of how much information there is in this distribution X. And then we could think of the conditional entropy as being, how much information we have in X once we know Y. And an important quantity that we get once we have both of these is so-called mutual information. The mutual information between X and Y is just the entropy of X minus the entropy of X conditioned on Y. So this is the idea of how much information about X is revealed by Y. Now, how do we bring this back here? Well, we get Shannon's definition of perfect secrecy. So what does this definition say? It says, well, we can start with any distribution on messages, but it should be the case that when we encrypt a message and we look at the information that's revealed by the encryption of the message, it should reveal nothing about the message. Oh, for any distribution on, you can take any, it doesn't matter what the whatever the a priori distribution is, it doesn't matter. It should be the case that the mutual information then between the C that we get by encrypting from that distribution doesn't reveal anything about M. Now, you may have seen this in a different form, which doesn't involve information theory at all, right? We could just say something like this. Right, the condition of the plain text conditioned on the ciphertext is just equal to the a priori distribution on the plain text. But we do get something here that we don't have in just that probabilistic statement. I mean, in particular, we have this quantity, this information leakage quantity, and maybe that's something that we'll find to be useful when we move to the computational setting. All right. Now, Shannon gave this definition, and it turns out that it's possible to achieve perfect secrecy. And in fact, there's this encryption system called Vernon's one-time pad, which was proposed in 1917. And the idea here is that the space of keys are just bit strings, which are as long as messages. And to encrypt a message, you pick a random key, you XOR the message with the key, and it's not hard to see then that when you XOR a fixed message with a random key, what you get just has the uniform distribution, and so that conceals all information. So is that the end? Yes?
What do you mean by XOR? Sorry.
Oh, XOR, a bitwise XOR. Addition mod 2, okay, yes. Yeah, addition mod 2, yeah. Bitwise. Well, one thing that this entropy formulation lets us do easily is to see the following. So suppose we have perfect secrecy. What does that mean? Well, another way of saying that is that the entropy of the plain text is equal to this conditional of the entropy of the plain text conditioned on the ciphertext. And now we just use some obvious properties of entropy, which I think are easy to see intuitively, so I'm not going to bother proving them to you. But clearly, if we added another random variable there, that's only going to increase the amount of information that we have. So we could say, well, that's less than or equal to the what we have if we add this extra random variable. Now we can use a kind of chain rule property that we have for entropy. So this is just the same thing as the entropy of M conditioned on both K and C, plus the entropy of K conditioned on C. Now, of course, the entropy of M conditioned on K and C tell us everything there is to know about M. So that just drops out. And of course, the entropy of K conditioned on C is always going to be less than the entropy of K. And so what this shows us is that in order to achieve perfect secrecy, it has to be the case that the entropy of the key space is at least as great as the entropy of the message space. Now, if you think of this setup, that means that in order for Alice and Bob to set things up, they basically have to exchange as much information beforehand as they end up exchanging when they actually execute the protocol. So this is certainly one drawback, or a big drawback of the information theoretic setting.
Did Shannon prove this?
Yeah. It's often stated in the form that the key has to be as long as the message, but this is sort of a more and this is like, it just works out so nicely with the calculations that it's a nice way of looking at it. All right, so now let's leave the information theoretic setting and fast forward to the computational setting. Okay, and now we're looking at the work of Goldwasser and Macaulay from 1982. Turing Award winning work among other work, but this is certainly a big part of it. So what's happening now is we want to start looking at things computationally. So first of all, we don't want encryption and decryption just to be arbitrary functions. We want a situation where the encryption and decryption functions are efficiently computable. Maybe they're allowed to use some kind of randomization. And we're never going to be too specific in this talk about exactly what these encryption and decryption functions are doing. But we just imagine, we know that there are lots of different ways of getting encryption algorithms that are efficient. But what we want to do now is to try to see what we can do as far as a security definition in this computational setting. So to start, we need to introduce a notion that's called indistinguishability. All right, so let's suppose that we just have two distributions now, x0 and x1. On some set. In fact, we're going to parameterize everything here. So in fact, we could think of having sequences of distributions, but to keep the notation simple, I'm not going to put indices on these distributions unless it's absolutely necessary. So let me try to give the definition of indistinguishability. So we're going to have two parameters here. Two parameters which depend on n. And we're going to say that x1 is T epsilon indistinguishable from x0 if the following holds. It should be the case that for every predicate, every 0, 1 valued function that maps the space into 0, 1, and also the case that, all right, so now D here, we're in this computational setting. Not only are the good guys computable, it's also the case that this adversary has to be computable as well. And so I don't want to dwell on this too much, but this means computable D should be computable by a circuit, a Boolean circuit of size t, where t, of course, depends on n. So the distinguisher here in this case depends on n, but for different n's, we could have different d's. So it's a little bit different from the situation we have with a uniform algorithm where we have one algorithm that works for every input size. Here we're just allowing the possibility that for different input sizes we could have different distinguishers. So it should be the case that for every distinguisher that's not too complex, its advantage, which we define as the following. All right, so what is this saying? What does it mean for these two distributions to be indistinguishable? Well, we'll take a distinguisher and, oops, this is a type, an error there. We'll take this distinguisher and we'll either give it a sample from the first distribution or we'll give it a sample from the second distribution. And it should be the case that if this distinguisher is computable by a circuit of size t, then its advantage in distinguishing whether it's in this first case where it's getting a sample from x1 or whether it's getting a sample from x0 should be smaller than epsilon. There's another way of looking at this which might make it a little more intuitive. An equivalent way of looking at this would be that we'll kind of do the following experiment. We'll flip a coin. So we'll pick this random z, and then depending on the outcome of the coin flip, we'll give the distinguisher a sample from one of the two distributions. And then if the distinguisher correctly, the probability that the distinguisher is going to be able to correctly guess which one of these two distributions the sample came from is not much better than he could do by just randomly guessing, right? Just say, I don't know, of course, if you flipped a coin, he would get it right with probability 1/2, but what we're saying here is that he really can't do much better than that. All right, so this indistinguishability notion is what we need in order to define security in the computational case. So now we go back to one of the definitions that Goldwasser and Macaulay gave for encryption security in the computational setting. And this is called message indistinguishability. and I'll just abbreviate that as MI. So we'll say that an encryption scheme is T epsilon message indistinguishable if for any pair of messages the encryption of the first message is indistinguishable from the encryption of the second message. Okay, and of course this is a probabilistic statement, which is getting hidden in the notation. Here we're taking a key that's chosen randomly, applying this encryption algorithm, which may be randomized, and then the distribution that we get, if we did that starting with x1, should be indistinguishable from the distribution that we get if we started with x0. So any questions at this point? No, it doesn't depend on the distribution of messages at all. Right, so that's looks different from the Shannon setting in some sense. Saying, yeah, well, we're down to just 2 messages here, which is kind of very powerful. In fact, we'll see in some of the proofs, if I ever get to them, how powerful this really is, this idea that, you know, really what it comes down to is the inability of an eavesdropper to be able to distinguish between, you know, that the eavesdropper could choose 2 messages, tell Alice to send one of them, and not be able to tell which one is being sent. All right, now I was going to talk about an asymptotic formulation of this. I'm not going to do that right now. I may have to come back to that later on, but let's just move along here. So now the question is, this looks pretty different from Shannon's characterization of encryption security. And so we may wonder, you know, is there some way of seeing a closer connection between the two? Now, Goldwasser and Macaulay actually propose another Shannon-like notion that they call semantic security. All right, and semantic security basically says something like this, that for any property of the plain text, we can't do any better computing it if we see the ciphertext than if we didn't see the ciphertext. So I'm not going to write down the definition of that, but so it looks a little bit like Shannon's definition, but it's not really clear if there's some sort of computational version of Shannon that comes out of this definition. But it turns out that around this time, in 1982, Yao proposed a different version of encryption security, which actually does use a kind of computational information. So Yao's definition basically said that an encryption scheme is secure if seeing the ciphertext, well, no, suppose we have a compression scheme where we're compressing messages from the plaintext space. Could we compress them more if our decompression algorithm was allowed to see the ciphertext when it was decompressing? And he's able to get a notion of computational information and a definition of encryption security based on this. And then later it was shown by Yao and also in more detail by Macaulay, Rakoff, and Sloan. That this compression-based notion of encryption security was actually equivalent to the notion of message indistinguishability. All right, well, so that's sort of what was known in terms of characterizing encryption security with respect to computational information. So now I'm going to move on and give a different approach, which I think is interesting and maybe a little bit more compelling than the definition that Yale gave based on compression. So now we're going to back up in time again. And this is where gambling comes into it. So in 1957, John Kelly wrote a paper that appeared in the Bell System Technical Journal called A New Interpretation of Information Rate. So Kelly was interested in entropy and mutual information, but he wanted to give a characterization which didn't involve things like error correction or what happens to the transmission of messages over a channel. So what Kelly considered is a situation where you have a gambler. A gambler is repeatedly betting on the outcome of these independent and identically distributed events. All right, and the goal of the bettor in the situation over this sequence of events is to maximize the expected rate at which his wealth grows. So it's not like in each individual race he's trying to maximize his expected return. What he's trying to maximize is the rate at which wealth grows over a sequence of events.
Or minimize the rate at which he loses.
Yes. All right, so the bettor in this case we can then just look at as a mapping from a set. I'll call the set of the set underlying the set of possible events M here, just to be consistent with what we're going to be doing. And now we introduce this assumption. So B of X is the fraction of wealth that the gambler places on outcome X. So of course, you couldn't, if you added those all up, they couldn't be greater than 1. But Kelly introduces this extra condition that, in fact, we want them to be equal to 1. So in every race, the gambler wagers all of his wealth across the possible outcomes. Now, that assumption in general might not be reasonable, but we're also going to assume that our odds function, the odds function telling us what the return is, what the track pays on each particular outcome, is fair in the sense that if we took the inverse of each of the payoff ratios, they add up to 1. So there's no track, so the track doesn't hold anything back, in other words, right? It's fair in that sense. And of course, with these two conditions, well, oh, I didn't say what happens. If you get outcome X, then the gambler is going to receive as a payment the fraction that he bet times the multiplier given by the odds function. And so with this assumption, if this is the payout, then the assumption that you bet all of your wealth is really without loss of generality, because you could just place offsetting bets with the wealth that you withheld, and you would get the same effect. All right, so now just to make this, forgetting about having this sequence of races, we can just state the condition much more simply, and it's going to be the same in the limit. Really, the goal of the gambler is to find a betting function which is going to maximize the expectation of the base 2 log of the payoff on the outcome of a random event. All right, well, can we figure out what that B should be? Well, let's just look at this expression. All right, well, of course, this expectation of the log of O of m is something that's fixed. That has nothing to do with the gambler. That's just determined by the odds function. But let's manipulate this expression here a little bit. We'll write out the definition. Oh, and one thing that I'm doing here that might be a bit confusing, if you look at B, B is like a probability mass function, right? It takes on values between 0 and 1. They add up to 1. So, we could equivalently view B as actually being a random variable or the distribution that has that associated mass function. So when I write B in an expression like this, I mean the distribution that has the mass function, which is given by this B. All right, after some simplification, we see that the expected payout has this form, this thing which I said we can't do anything about. Also, an expression just involving the entropy of the underlying event. And then finally, this expression here, where this is what's called the information divergence. All right, and this is a well-studied, KL stands for Kullback-Leibler, in honor of the statisticians who created this, this notion, but we're going to use some properties of the KL divergence, which just come out of simple kinds of convexity considerations. So the information divergence is always non-negative, and actually achieves a value of 0 when x is equal to y. And we'll need to consider a conditional version of KL divergence as well. So let me just write that down here. Right, we can think of the information divergence between two conditional distributions. And one important fact I'm going to use here is a so-called chain rule, which says that it gives us a relationship between the conditional KL divergence and the KL divergence of the corresponding joint distributions. The important case is when x and y are equal. So So usually I'll write these expressions just in terms of the joint distribution rather than writing them conditionally like that. That'll come up later. But anyway, getting back now to Kelly's situation, well, how are we going to maximize this expression? Well, the only thing we have control over is B. We know that the KL divergence is always non-negative, but achieves the value of 0 on that case. So we just take to get the maximum, the best that the gambler can do is just to look at the a priori distribution on outcomes and bet proportionally to what that outcome, the probability of that outcome. All right. Now where it gets interesting, I suppose, is now let's suppose that, see, clearly the gambler isn't doing very well here. So let's try to give the gambler some advantage by giving him some inside information. So what we're going to do is we're going to assume now that we have this random event happening and that the outcome of the event is transmitted on a channel, say to the bookie, And now the gambler is eavesdropping. Now in Kelly's setting, he wasn't thinking about encryption, but he said, suppose that the information that the gambler is getting is noisy in some sense. All right, so what happens here is that some X is sent. The gambler actually sees a value Y, and what the gambler is going to do is to have a betting function where for each particular Y that he observes, he'll have a value that he bets on any given X. So of course, we still need something like this, that for any given Y, we have one of these betting functions. And so we still want the wealth that's bet once a Y is observed to add up to 1. All right, well, I'm really going much more slowly than I wanted to, so let me try to summarize a bit here. What we're really worried about in this situation now is how much better can the eavesdropping gambler do than a gambler who didn't have any inside information? So without too much work, we can see that, well, first of all, that the advantage is something like this. This is the advantage that an eavesdropping gambler has over an honest gambler. And in fact, and let me just write down what we can simplify this to. And so the max advantage is actually going to be given, well, it's actually going, this is going to drop out again, right? Because the gambler, again, can just use the a priori conditional distribution, and we get the max advantage then is so in other words, the maximum advantage that this eavesdropping gambler has is just the mutual information between the actual event and the noisy version of the event that the gambler gets to see. Now, surprisingly, Kelly, although he was saying that he was trying to find, other ways of characterizing mutual information, never mentions encryption in this case. But it's not hard to see that if the way that C arises is as an encrypted version of M, then what we get out of this is that a way of characterizing perfect secrecy is that in this situation, it gives the eavesdropping gambler 0 advantage. All right. Well, it's pretty easy now to move this into a computational setting. All right, so this is, maybe there's like a double lost opportunity here. Not only did Kelly fail to connect this to Shannon's theory of secrecy, if he had been listening to what Turing said in 1950, maybe he would have thought, well, this is an easy way to think of what happens in a computational setting, and we might have had computational cryptography 25 years earlier. So no historians at this talk, so I can indulge in alternate histories. I think that's okay. All right, so all right, but I'm really running out of time, so I'm just going to say a little bit about this, do one proof to give you a flavor of what's going on, and then try to summarize the rest of the results that we have. So this computational setting is work that I've done with my student, Mohammad Hajiabadi. And what we're going to do is we're going to characterize security in terms of this advantage with respect to a resource-bounded gambler. So again, now we're going to be in a situation where our gambling function is computed by a circuit of size t. And so this computational notion of security says that the advantage of a gambler, assuming that the gambler has a limited size, is bounded by epsilon. Oh, sorry? Yeah, H of M should be here because H of M, if I had worked out the definition here of the advantage of an eavesdropping gambler, the H of M would stay in that expression. Do you want me to work that out, or do you want to? No, yeah. Yeah, yeah. Oh, yeah. This term's negative. This term's negative. Yeah, yeah, yeah. Right. I mean, yeah. It would have to be, I could do a 1 over this and then do minus. Yeah, yeah. All right. So, so one result that we have is that, and I'm going to leave out the parameters here, but essentially the result is that gambling security is identical to message indistinguishability. All right, so we have this way of characterizing encryption security. We're basically using a proxy for mutual information by introducing this advantage of an eavesdropping gambler. And this gives us something which is equivalent to message indistinguishability. So let me just try to take the time to do one part of this proof. So one direction. That gambling security implies message indistinguishability with some, of course, change in the parameters. So we're going to get delta to be something like 2 ln 2, square root of 2 ln 2 epsilon, and t prime So what you see is that there's some loss in security here, right? Having epsilon gambling security gives us something like square root of epsilon message indistinguishability. and only against adversaries that have somewhat less time in order to do the distinguishing. Exactly, yes, right. And it's pretty nice, actually. So let me do the proof. It's not that long. So say they weren't message indistinguishable. That would have to mean that we have a distinguisher and a pair of messages that the distinguisher can have good success with. All right, so we get the distinguisher gets the encryption of a randomly chosen message, has to decide which one, and can't do that much better than guessing. Can do it, yes. Can do it much better than guessing. And this should be delta, right? Right, can do it much better than guessing. All right, well, now what do we need to do? We need to find some distribution where the gambler has good advantage. So what is this distribution going to be? Well, it's just going to assign probability 0 to any message other than x0 or x1. And then it's just going to, for the other ones, it's just going to give them probability 1/2. OK, now what we need to do is to define our betting function. One thing that I should say here is that, as far as the gambler is concerned now, we've moved from the setting of a horse race to a coin flip, right? So now we just need a gambler that has good advantage for a coin flip, where he's getting some inside information about whether the result is heads or tails. All right, well, he knows to bet 0 if x is outside of the possible outcomes. Otherwise, what does he do? Well, he feeds, yes. Depending on he looks at what x is, and he sees whether or not, when he feeds y to the distinguisher, y gives an answer which is consistent with the x value that he's seeing. In that case, he's feeling more confident that it would be that value because he's relying on the help of the distinguisher. So he's going to up his bet by a additive term of delta here. Otherwise, he's going to decrease his bet by delta. So now it's pretty easy to calculate. All right, well, in this case, h of m, the entropy of the distribution is just 1. And this value comes out to and here, this is like the negative of the binary entropy function. And with a little bit of calculation, just say we could do a series expansion of this expression, and we get that the better's advantage is basically bigger than delta squared. And so starting off with a distinguisher whose advantage is delta, we get a betting function whose advantage is delta squared. All right, well, I think because of time constraints, I'm going to have to stop here. But happy to take any questions.
Thank